In our previous tutorial, we discussed the motor inputs as well as a little bit about the dynamics on and how the operational starting control and the different options worked. In this tutorial, I want to focus on the operational and the emergency stop, as well as how we use brakes in Sidewinder. So at this point right now, we simply said, okay, in the operational stop, in other words, a normal stop condition, power is available, we're going to just turn off the motors and drift to a stop. And in an emergency stop, say in a power failure condition, we're also going to drift to a stop. And when we run the calculations, we can see our fully loaded normal friction case is stopping in about 21 seconds. The empty belt stops in about 25. If we have the inclines loaded, it's about 12 seconds. And if we have the declines loaded, hey, there's a problem here. Well, if we look at that loading case, just this decline section here, loaded, we're actually at a demand power of minus 40 kilowatts. Now, in our conveyor design, we would have had to look at this condition and say, hey, when we select our motor type, we're either going to have a 4-quadrant motor that can deal with regeneration, or we got to have regenerative braking, or something to deal with this regeneration case, and that's what Sidewinder is kind of warning us about here. So what would be our options? Well, we've got VFD drives on this conveyor. Again, this is just a fictitious conveyor I'm using, but it's a nice conveyor because it demonstrates a lot of these points. I could say, hey, in an operational stop, if we've got power available, let's go ahead and use the motors to decelerate the conveyor in 20 seconds. Okay, well, if I do that, it's going to take about 40% motor torque, and our tension ratios are actually acceptable. So we could specify in an operational stop operational stopping time of 20 seconds. And we can also see here that our sag is acceptable and our safety factors are acceptable in that condition. We can look at some of our other cases. For the incline case, alright, that takes about 29% motor torque. For the fully loaded case, it's actually minus 3%. Well, if we remember, our drift time here is 21 seconds. So if we're stopping it faster than the drift time, our motor torque is actually going to be negative. If I make it longer than the drift time, say 25 seconds, we can see that value is now positive because we're longer than the drift time. So that's how the used motors to decelerate the conveyor works. That would be with a wound rotor motor, a variable frequency drive, or the variable speed fluid coupling. Any of those, you can use the motors to ramp the conveyor speed to bring the conveyor to rest. Now, in the emergency stop, however, hey, in that case, once we lose power, we don't have power. So we obviously still have some issues here with this decline load case when we have an emergency stop. So in that case, let's go ahead and apply the maximum braking torque. Well, what have we specified? Well, first let's look at our geometry. And what we have is we simply have a brake at the tail. So if I go to the tail pulley here, I can see we've got a single brake pulley there. Okay, so we've got a brake pulley there. If I look on my brake page, I've specified that as a low-speed brake. Obviously, there's no gearbox or motor there, so it's got to be a low-speed brake. I'm going to say there's just one brake on that pulley, which is the default. Actually, if I didn't specify that, it would have used one. And I'm going to put a maximum braking torque of 15 kilonewtons. So if I go back to my dynamics page here and I run this, we can see 15 kilonewtons will stop our decline load case in 16.5 seconds, and our tension ratios are also fine. Now we obviously need to check our incline case. Okay, our incline case, that stops it if our inclines were loaded and we had an emergency stop. That also still applies to 15 kilonewtons, and it's going to stop it in 8 seconds. Fully loaded, it's going to stop at 11.3 seconds. So by just saying use the maximum braking torque, that will simply use this braking torque, keep this constant, and change our stopping time. The other option that we actually have here is we have apply brake torque required for deceleration time. So this is more for if you'd have a proportional brake. So I could say, for example, 10 seconds here. And when I run this, what this will do is it'll simply calculate, it will calculate the brake torque required to stop the conveyor in 10 seconds. at a maximum of what I've entered here. So actually 10 seconds at the full 15 kilonewton, it takes 11. So I either need to increase my brake, or let's just make this 20 seconds just for example purposes here. Okay, in 20 seconds it only used, well, it's actually about 0.2 kilonewtons. Let's say 15 seconds there. To stop the conveyor in 15 seconds, it's taking 5.9 kilonewtons. For the incline case, well, it's not taking anything because it's already drifting to a stop in 12.7. For the decline case, there I've maxed it out again. It's taking 16.5 because the most it can do is the 15 kilonewtons. So if I really wanted a deceleration time of 15 kilonewtons, I might actually have to change this to say 20, or, well, obviously I need more than 15. Let's just say 20 once. Go ahead and run it. Okay, I need 16.3. So let's say 16.5. That gives us a little bit extra. So there we go. So our 15-second stopping time for the decline case is almost full braking torque. For the incline case is nothing. For the fully loaded case is, roughly 6 kilonewton meters. So that's how that works. So that's your options. You can drift to a stop, apply the max brake torque, or apply the torque required for the deceleration. And you can also use these in conjunction with the operational stop. That might be the same thing. In an operational stop, maybe we say normally we'll stop it in 25 seconds, but in an emergency case, somebody pulls the pull cord or you have a power failure, we're going to stop it in a little bit faster, say 15 seconds. So there we go, fully loaded. Again, we specified 21, so it'll just drift to a stop. The incline case drifts to a stop. The decline case, okay, 25, it applied 10.6 kilonewtons, and in the e-stop, almost a full. So it's pretty nice. Sidewinder's pretty powerful. Gives you a lot of flexibility there. Going back on the brake page here, if, for example, if we had a brake on a motor, or let's even say that our motor, we've got a single drive pulley, but let's say we had two motors. Okay, so we've got two motors, and just for example purposes, I'm going to change my tail pulley here, or my tail brake to a pulley, and I'm going to put the brake on this primary motor. So I'm going to say that that is actually a motor, a brake, and a backstop. So go ahead and set that. I go back over here and I go to my brake page. Now I could specify whether that is going to be a low speed brake, i.e. it would be between the reducer and the head pulley, or I could say, hey, let's put a high speed brake on there, which is going to be between the drive and the reducer. So my reducer is going to work for me. I can then again specify whether I've got one, i.e. it's only on one of the motors, one of the two motors, or I can say let's put it on both motors, and let's put, I'm just guessing here, let's pick a 1,000 Newton meter brake. So each drive right now has got a 1,000 Newton meter high speed brake, and I'm going to select to simply apply the max brake torque in each of these cases and run the calculations. Well, we run it. Well, let's just go through each of our cases. Empty, oh, we got some drive slip problems. Fully loaded, still got some drive slip problems. Declines, we're stopping it in 13 seconds. Well, we said just a minute ago we only want to use maybe 15 seconds. So let's reduce that. Let's probably only needed 500, or in fact, let's just put one high-speed brake on instead of two. There we go. So now the decline load case is stopping in almost 30 seconds. So again, we can play around with this. If we want to stop that in 15, we'd need, maybe we'd say, go back to 2 and put on two 750s, or we could go with one 1500. What's that give us? 18 seconds. Pretty close. Our incline load case, it's stopping in 8 seconds, but our tension ratios are still okay. Our fully loaded case, we're stopping in 11 seconds, but we might be getting into some sag problems here. So with our fully loaded case, when we're stopping, we're braking it. Now you got to remember at the head, we might be getting into some sag issues here. So these are all things you're going to have to play around with on the conveyor. So we needed, we needed enough braking torque to stop that decline case, and maybe maybe we could say our 1,000 was okay, and in that decline load case it's going to take 30 seconds to stop. Just depends on the conveyor and your design criteria. But these are how you can work with Sidewinder. Look at a tail brake versus a high-speed brake at the head, or a single brake versus a double, and your tension ratios. Sidewinder is very powerful to let you kind of quickly look at these different cases and scenarios and see if there's any problems. It's also a good idea to just, obviously you got to go through your cases, but if you click on your project case page, you can a lot of times see if there's any problems or any issues anywhere, rather than clicking through each one of these cases. You can see here if I had set this at 2,000 and ran it, and I was looking at, well, the fully normal load case is a problem here, but if I click on my project, I also can quickly look at all of the cases to see if there's any problem. So Sidewinder is quite nice that it sort of highlights and lets you know if there's a problem. But of course, at the end of the day, you got to be a competent conveyor engineer as well. So I think that wraps it up for the dynamics and sort of the motors, reducers, brakes, and dynamics to this point. And we will continue on with the next tutorials in a minute.